Hello and welcome back again on a lecture series of engineering thermodynamics subject. My name is Devinder Singh Thapa, Assistant Professor in Mechanical Engineering Department of Silver Oak University. This is your third module. In previous two modules we completed two chapters. In module 1 we discuss about the basic introduction to the thermodynamics subject. In chapter number 2 we discuss about the first law of thermodynamics and its applications. So now in today's module, that is module 3, we will discuss about the second law of thermodynamics and its application. So we will start with our topic of second law of thermodynamics. Now before going to the second law of thermodynamics, we will go through the limitations of first law that we already discussed in our last lecture. So there were a number of limitations in the first law. Only because of that we have invented second law of thermodynamics. Now first law was your quantitative law, that was completely a mathematical law in which everything was defined in terms of mathematics, whether we get a result from Joule experiment, that is summation of Q barabar summation of W for a cyclic process. So all those things were in quantitative terms. Now in second law we will discuss about the qualitative terms, like directional law we will call second law sometimes. Now what were the limitation? The very first limitation was it does not help to predict whether the certain process is possible or not. Means first law was not able to give about the feasibility of the process. Although it was saying that some amount of heat will be transferred into some amount of work, or work will be transferred into heat, but it was not able to give you the feasibility for the process. Okay, now second limitation was it does not give you any information regarding the direction of flow, in which direction it will flow, from high temperature to low temperature or from low temperature to high temperature. So it was not giving you the direction. Only second law will give you the direction for flow of any heat or work. It does not provide and specify sufficient condition to process to take place. Again same, it is regarding the feasibility point. So these were the limitation of the first law that is being briefed in detail. So what first law says, that work is completely converted into heat, or heat is completely converted into work. So heat and work were mutually convertible, that we saw in the Joule experiment. But by experience or by in real world, this is not possible every time. Work can be completely converted into heat because work is a high grade energy and heat is a low grade energy, but complete conversion of heat into work is never possible. That today we will study in second law of thermodynamics. Is it clear? Now moving forward, so these were the points that we discussed in first law. What are the interpretation from first law? That it says work can be converted into heat, or heat can be converted into work. First law makes no distinction between the forms of energies, means it will not differentiate between kinetic energy, work or heat. It is just simply convert one form of energy into another form of energy. It is not sufficient to predict whether a change will or will not undergo a particular change. Means it was again it is regarding the feasibility, that it will take place or not, it will not tell by the first law. First law is a necessary condition but not sufficient condition for a process to take place. Although it is a necessary that it is this law need to be followed, but it is not a sufficient condition. And what is the sufficient condition for a process to take place? It will be your second law. So these are the interpretation that you will finally going to get after this lecture, that it indicates that second law indicates that all heat cannot be converted into work. Some form of heat will be rejected to the surrounding. Is it clear? According to second law, heat will not only transfer from high temperature to low temperature and not vice versa. So naturally, always you know that temperature always heat always flows from high temperature to low temperature. Water always flows from high head to low head, and inverse in nature. Naturally means without any external effect, always the direction will be from high head to low head, or high temperature to low temperature. But second law gives you the feasibility that heat can be transferred from low temperature to high temperature by using some external source like your pump or refrigerator. So that is possible only in the second law. Clear? So a cycle can occur if it satisfies both first law and second law. So both the laws need to be satisfied in order to have a cycle process. Okay, so it is a quantitative law and second law is a qualitative law. So another name for these laws that you have to remember. Okay, now we will go for the detailed study of second law. Firstly, we go through some of the terminologies that we will be using. One is your energy reservoirs, especially in thermodynamics subject. This thermal energy reservoir is important. So these are the large bodies. This is your source or this is your sink. All these two things are your thermal energy reservoirs. Is a large body of infinite heat capacity which is capable of absorbing or rejecting unlimited amount of heat. Means infinite capacity of heat these thermal reservoirs are having. So whatever amount of heat you want to add, you can add. Its temperature is going to remain constant. Means even after you add 1000 2000 kgs kilojoule of heat, still the temperature of this reservoir will be remaining same. This is the definition for thermal energy reservoir. All the processes are quasi-static that we have already discussed in the first lecture. Quasi-static means the processes in this that will occur in this reservoir will be reversible one. So thermal energy reservoir definition is clear. Then we will go for these are the terminologies. One will be your source, another one will be your sink. So we have given two names. One will be source that will be supplying heat to the heat engine, and one will be your sink. A sink can be atmospheric or river or sea, where you can reject out the remaining heat. I leave about the mechanical energy reservoirs. We are only focusing on thermal energy reservoirs. Clear? So now we are in a position to go for the second law of thermodynamics. So firstly I will define the second law. It gives the information about the thermodynamic processes. It may be defined as the heat cannot flow itself from cooler body to the higher body. So second law of thermodynamics basically give you the direction of flow of heat. It is a qualitative law that will give you the feasibility of the process. Actually the process is possible or not, it will only tell by the second law of thermodynamics. Again some scientists were there like Kelvin, Planck, two scientists were there. They have given you the definition for second law. Then one more scientist, Clausius, he has also given the definition for second law. So both the definitions are important and both are equivalent to each other. So Kelvin Planck statements are basically for power producing devices like your turbine, heat engines, IC engines. Those are giving you the power or electricity. So those devices will be defined on the basis of Kelvin Planck statement. And then we have a Clausius statement which will be defining you the daily devices like refrigerator, television, heat pump you are using for the definition of second law of thermodynamics. So firstly we will go through the Kelvin Planck. I will explain you in detail, then we will go for Clausius. Kelvin Planck statement that it is impossible for any device has heat engine that operate on a cycle to receive heat from a single reservoir and produce net amount of work. So both are the negative statement. They have given you the negative statement, then they prove that statement wrong, same as you are doing in mathematical induction topic in mathematics. So they both were the negative statements. It is impossible, directly saying that it is not possible that any device will work with a single source. So I will explain with the diagram. So this was your Kelvin Planck statement. What he said, this is the condition that was impossible. Means if any heat engine will not operate by a single reservoir, means there will be a heat engine only a single source or a single thermal energy reservoir. Having these two conditions is impossible said by the Kelvin Planck. Means you are supplying some amount of heat to the heat engine and you will get the net amount of work. Suppose I am supplying 5 kilojoule of heat, then I am getting directly 5 kilojoule of work. It is impossible. Otherwise, had this been possible, then your efficiency will be 100%. Means your automobiles or your engines, heat engines will operate with 100% efficiency. Means by putting 1 liter of petrol, you might go for 100 kilometer, and that is absolutely incorrect. This is not possible in real world. Some amount of heat in the form of pollution or noise, it will be rejected to the surrounding. That will be the ultimate condition. So it is impossible. This condition is completely impossible as said by the Kelvin Planck. So now what is possible? So what was the solution he has given? So if this is impossible, then what is possible? that I will show. This was the exact possibility that this will happen in actual world. So you will have a one source, and then definitely you are going to have a one sink, and you will supply some amount of heat to the heat engine. Heat engine will do some amount of work, and remaining heat will be rejected out to the surrounding. So this is your practical device or practical heat engine that is actually working in uh, our world. So this heat engine will be ideal one, or it will be actual practical one, and this is impossible as said by the Kelvin Planck. So what he ultimately concluded that for a heat engine to operate properly, it has to have a two thermal energy reservoir. One will be source, one will be sink, and then only your heat engine will properly work. So this was the statement of Kelvin Planck, in which we have studied about the heat engine. Now in upcoming slides, I will be giving you the detail regarding this heat engine, how these heat engines are working, how to calculate the efficiency. But before that, I will give you again same perpetual motion machine of second kind. It means the those types of machines which are violating the second law. And let me assure you, there are no machines which will no machines that are existing that are violating the second law. Had any machine possible to violate the second law, then it will be ppm2. Clear? So what ppm2? ppm2 means your efficiency of your heat engine will be 100%. Means you will have only one reservoir by which you will be supplying heat, and you are getting some amount of work. There is no heat rejection to the surrounding. So this is impossible. So this PMM2 is impossible, but still you have to remember the definition for PMM2. Clear? So this we concluded the Kelvin Planck. Now we are going for the Clausius statement for second law. Firstly, the definition for Clausius statement: heat always flows from a body at a higher temperature to the body at a lower temperature. This is a natural phenomena. Reverse process will never occur spontaneously. So if you have to supply heat from low temperature to high temperature, it is not going to occur naturally or spontaneously. We have to do some amount of work on that system. So it is impossible to construct a device which operating in a cycle will produce no effect other than transfer of heat from cooler body to the higher body. So spontaneously or naturally we will not, it is impossible to transfer heat from lower temperature to higher temperature. This was again the negative statement of Clausius, that it is impossible for a machine working in a cycle unaided by an external agency to convert heat from lower temperature to higher temperature. Means naturally your heat is never going to flow from lower temperature to high temperature. So this T1 source is at a higher temperature, T1 at lower temperature. So it is impossible to transfer heat from this to this naturally. So now this was the statement. Now for that solution, what he has given, he suggested that some amount of work, if this is possible only when you do some amount of work on that particular pump or a refrigerator. So these are power consuming devices that are consuming electricity in order to function. Now what this heat pump will do, it will take some amount of heat from this lower temperature body. Some amount of work will be done on the heat pump or a refrigerator, whatever you want to install. Then only it will supply that heat to the high temperature body. Clear? Then this will be your proper statement, or this will be a proper working heat pump or a refrigerator. Clear? So again, these two are the negative statements, but they are equivalent to each other, and only those statements are satisfied, then only your second law will be completed. So two types of devices we have studied. First one was your power producing devices like heat engine, whose statement was given by Kelvin Planck. Now second devices in mechanical system or in this whole world are power consuming devices, and those definitions was given by Clausius scientist. Clear? Now there are two types of devices for Clausius. One will be your heat pump, another one will be your refrigerator. Both are the same devices that will do the same work, that is they will transfer heat from lower temperature body to the high temperature body, both heat pump and refrigerator, but their desirable effects are different. In heat pump we need to warm the room, or this source will be your desirable effect. in a refrigerator your sink will be desirable. Desirable means what do you want? In refrigerator we want to have a cooler conditions as compared to our surrounding condition. In room heater what do you want? We want higher temperature as compared to the surrounding temperature, but their functioning will remain same, that we will supply Q2 from T2, Q2 from T2, then we will do some amount of work on the system, then it will supply heat to the high temperature body. Functioning is same, only their desirable effect is different. So this is a complete setup for refrigerator RAC that you might have gone through in BME subject, and this is used to maintain the room temperature at a lower temperature as compared to surrounding. For AC, for refrigerator we want our refrigerator, inside the refrigerator we want lower temperature as compared to the surrounding temperature. Now these are the parameters or the devices like refrigerator or evaporator. We have a compressor, we have a condenser, then we have a throttling valve. So the desirable effect will be in this area where it will be rejecting out its heat and getting the temperature cooler as compared to the surrounding temperature. So detail you will go through in your next semester subject refrigeration and air conditioning. Here I am just giving you the brief in order to understand the second law of thermodynamics. So all these devices are working on the second law of thermodynamics. So these are the two devices for Clausius statement, refrigerator and heat pump. Again they are doing the same work. This is lower temperature, this is cold condition, and they are taking out heat from lower temperature and giving to the higher temperature, taking out heat from low temperature, giving it to the high temperature, but their desirable effects are different. In heat pump we want warm conditions, in refrigerator we want cooler conditions, but their process of functioning will remain absolutely same. Clear? So this is now these are the expression how to define the COP, desirable effect over the work input. So what is desirable effect for heat pump? This T1 will be your QR will be your desirable effect. For refrigerator this T2 will be your desirable effect, or work will remain same for both the conditions. These are generalized formula that you will easily able to understand. Now heat pump, again heat pump same, COP, coefficient of performance for heat pump will be again desirable effect over work input. What is desirable effect? Desirable effect is your Q1. So Q1 divided by W. W means what? By this is a cyclic process. We will apply the first law of thermodynamics. Summation of Q barabar summation of W. W will be equal to how much? Q1 is heat added to the system minus Q2. So we can write, instead of W we can write Q1 minus Q2. So this is your formula for COP of heat pump. If you do the calculation, then this is an important correlation. COP of heat pump will be equal to 1 plus COP of refrigerator. Always COP of heat pump will be higher as compared to the COP of refrigerator. So this is your mathematical proof. So this concludes your first section, that is Clausius. Now again heat engines are there. This is comparison between these two. Kelvin Planck is used for heat engines. Clausius statements are used for power consuming devices like heat pump and refrigerator. Then both are negative statements and both are experimental data, that is clearly understood. Now second portion, that is heat engines. How we will define heat engines? What are the applications of heat engine that we are going to study now? So heat engine is a device which work in a cycle, convert energy in the form of heat into work. So heat engine, as by the name it is clear that it is related to heat. So here we will be studying about the conversion of heat into work. How much amount of heat you are able to convert into work, that will give you the efficiency for any heat engine. So these are characterized by they have convert the part of heat into work, they reject remaining part to the surrounding, that we have already seen. They operate in a cycle. So this is a typical heat engine. All your engines are heat engine type, whether it is a steam engine or it is a gas turbine engine that we are going to study. So this is a typical heat engine, in which a steam engine that is having a boiler. You might have gone through BME subject. Boiler produces steam, and that will operate the turbine, and it will give you the turbine work. Then remaining steam energy or heat will be rejected out in the condenser, and that it will be converted, steam will be converted into water. That water will be pumped by the device pump, and that will again supply the water into the boiler. Same manner again boiler will convert it into steam, and this process will be repeated. So this is a cyclic heat engine which are having 4 components, and by which you are getting some amount of turbine work, and the turbine will be connected to generator, and it will lead to the generation of electricity. So this is a typical diagram for any heat engine. It can be a gas turbine engine or it can be a steam engine. Clear? So these are the mathematical expression. By balancing the heat and work, you are going to get the efficiency, that is net work over heat supplied, heat input. So what is your net work? W. And what is your heat input? You are supplying heat at the Q1 section, that is your source Q1. So you will divide by Q1, then this become 1 minus Q2 by Q1, and the efficiency is somewhat around 30 to 40% in heat engines. So heat engine is this is your efficiency. It's the application of Kelvin-Planck statement, in which we are going to get the efficiency, what is the ratio of work done over heat supplied. So this is all about heat engines. Now what we are going to do now, the one of the practical examples regarding your heat engine, one will be your Carnot heat engine. You know about the word Carnot cycle. So it was invented by Sadi Carnot in 1824, which work on a reversible cycle. So what it says, that it will have a 4 process that we have already gone through in previous slides. Same, the working of this Carnot cycle will be that it will have a source, it will have a sink, then it will have a working device. It may be a IC engine or a piston cylinder arrangement, in which our working fluid or working substance like fuel will be burned inside the system. It will generate some amount of heat and it will do some amount of work. So all the processes of these will be having reversible process. Carnot cycle, ideal cycle we have understood. So it will comprise of 4 processes. One will be your reversible isothermal, and that is heat addition process. Then we have a adiabatic process, expansion process, again isothermal heat rejection, and then finally we have a reversible adiabatic or isentropic compression process. So 2 will be isentropic processes and 2 will be your isothermal processes. That is your Carnot cycle. So these are the processes that have been plotted in PV diagram. So this is the proper working. Firstly, we will supply heat to the system at isothermal process. Then it will do some compression work. Your fuel will be compressed. Then we have a power stroke or expansion process where work will be done WE. Then again it will reject out heat isothermally to the surrounding. So these are the 4 processes, 2 isothermal and 2 reversible adiabatic, or we call that an isentropic process. Clear? So 1 to 2 process is your isothermal heat addition. This is your 1 to 2 process. This is your 1 to 2 process, isothermal constant temperature heat addition process. Then we have a 2 to 3 expansion process, isentropic or reversible adiabatic process. Then again 3 to 4 heat rejection process, and finally we will have a 4 to 1 again isentropic or reversible adiabatic compression process, denoted by WP. This is your compression process, where your piston will be pushed inside and your fuel will be compressed. So typical Carnot heat engine, again efficiency we have studied, it is nothing but what? Again 1 minus Q2 by Q1, efficiency formula for every heat engine, whether it is a Carnot heat engine or it is a steam engine, everywhere the formula for efficiency will remain same. That is, basic formula is net work done over heat supply, that we have studied in the previous lectures, okay, previous slides. Now this is your heat engine. Another heat engine, or there are number of heat engines that we will study their example, but before that we are going for a Carnot theorem. There are basically 2 Carnot that we have studied. Carnot the cycle, the Carnot analogy or the conclusion of second law of thermodynamics, it says 2 statements, and their proof we will discuss. That all the reversible heat engine operating between 2 constant temperature have the same efficiency. If there are number, suppose we have a number of heat engines, suppose 1 2 3 4. If their temperature are constant, T1 upon T2, temperature limits are same, then you put any number of heat engines, reversible heat engine 1, heat engine 2, then all will have the same efficiency. This was first conclusion of Carnot theorem. Secondly, the efficiency of reversible heat engine will always be greater than all the irreversible heat engine. This is your second statement. So these are the two conclusions from your Carnot theorem that we have to remember, and their proofs are also there. So slowly we will just go through the proofs. And this is the first proof, that all the heat engine operating between a given temperature source and sink, none has a higher efficiency than a reversible heat engine. So it says that always your reversible heat engine will be having higher efficiency. So what we have taken in our lecture, in our theory section, that we are trying to prove this one. So we will take one as a reversible heat engine, one as a irreversible heat engine. Then we will start with the saying that irreversible heat engine efficiency is higher. Then finally we will prove that no, this is not possible. So a reversible heat engine proof will be higher, efficiency will be higher as compared to irreversible heat engine. So this was the typical process that we have applied in induction. So proof is just go through the proof that we have discussed in the previous lectures. So next one is efficiency of all the reversible heat engine operating between the same temperature thermal energy reservoir will have the same efficiency. So this is another statement of two important statement from Carnot theorem that we have to remember. One is between same temperature limit all the heat engine will have the same efficiency, and another one is the reversible heat engine will always have a greater efficiency as compared to irreversible heat engines. So same manner, now number of Carnot heat engines that are Otto cycle, petrol, diesel engines, dual engine, Brayton engine, or Carnot cycle. Recently we have discussed, and then steam or Rankine cycles are there that we have to study in detail. So firstly, in today's lecture we have a shortage of time, then I briefly give you one type of cycle or one type of heat engine, then rest things we will cover in our cyclic chapter. Rest cycles we will discuss in the cycle chapter. Maybe next lecture I will be conducting on these cycles, but today we try to go through the Brayton cycle or Brayton heat engine, how it is working, what are the processes that we discuss. So gas turbine engines are again operating on the same parameter that we have discussed in Carnot. It will have 4 processes, and what are those 4 processes that we will discuss in detail. So these are the 4 processes. PV diagram. Again, 2 will be your constant pressure instead of constant temperature or isothermal in Carnot cycle. In Brayton cycle we are having 2 constant pressure processes. This is one PC and this is your AD. Heat addition and heat rejection are occurring at the constant pressure instead of isothermal. This is the major change or only change in Carnot and Brayton cycle. So Brayton, what he did, he added the heat and removed the heat at constant pressure, and rest 2 processes are isentropic or reversible adiabatic process. Rest 2 are remaining same. Now we are going for the detailed elaboration of this process, how the heat addition and rejection and work done are been occurring. So first we have a compressor, then we have a heat exchanger, turbine and heat exchanger. This heat exchanger can be any power producing, and this will be a sort of condenser where your heat rejection will be occurring. Okay. So now the process is defined by 1, 2, 3, 4. 1, 2, 3, 4. Again, this is your PV diagram. So process number 1 to 2 occurring, that is your compressor process. What is happening in compressor? We know that always some amount of work has to be added to the compressor. So 1 to 2 will be isentropic compression process. Means reversible adiabatic manner, you will be doing some amount of work on the compressor in 1 to 2 process. Then now in 2 to 3 process, what is going to happen? We are going to add heat to the gases. That particular gas we are going to add heat. So if your gas is the medium in gas turbines, so 1 to 2 you have compressed, then we are adding heat to the particular medium working substance. So then after heat exchanger, what is going to happen? It will that heat will be supplied to the turbine, gas turbine. 3 to 4 process will be isentropic expansion process, or WNet or turbine work we are going to get WT. So 3 to 4 will be your isentropic turbine work output you are going to get. 3 to 4. This is our animation. Again, the processes are very simple. So this here we are going to get the net work output or positive work we are going to get in the turbine. After that, that particular medium or working substance will pass through another heat exchanger, that is your condenser, where it is going to reject out the remaining heat to the surrounding. So this photon again, we have reached to one point. So this completes your cycle, that is your Batten cycle, where this process will be number of times it will be repeated and you are going to get the net work output. So this is how your Batten cycle is working. These are the four. Again, we have combinedly I have given the 3D images of compressor, heat exchanger, turbine and heat exchanger, and this is how the process is been occurring. So in this manner your general gas turbine is working, or the typical type of heat exchanger or different compressors or turbines are working. So this is the working of gas turbine. Another type of heat exchanger or heat engine we have studied. So this is the working. So we concluded this topic now. This is how the second law is working. Their practical application we have gone through. Different types of heat engine I have given you: the Carnot heat engine, gas turbine heat engine. Then we have discussed about the different types of power consuming devices or Clausius statement, that is for refrigerator we have studied. We have studied in detail regarding the how the functioning of heat pump is occurring. So in this manner we have concluded the second law. Only the single portion of second law, that is the application of second law, is there, that is known as entropy. You might have heard about the term entropy. Energy term is frequently used, but entropy term is not frequently used. So in your maybe in your next lecture I will go for the some types of cycle like Otto cycle, diesel cycle, or we will hold on that topic of cycles, that we can go for entropy in your next lecture. So entropy, one of the application of second law that we will be studying in your next lecture, followed by the exergy or available energy that we will be discussing in our next lecture. Okay. Now, thank you for attending the lecture. If you have any doubt or query, you can directly contact me regarding the second law. Otherwise, keep on practicing the things, try to revise the topic of second law, and then we will meet in the next lecture. Thank you for attending the lecture.